Hello all, welcome to this video on theory of computation. Today I'll be talking about alphabets, strings and languages. Let us begin with the introduction. For more than 50 years, as computing systems have diminished in size and grown in complexity, theoretical computer scientists have built the foundations of their discipline by developing models of computation and related methods of analysis. After the early recognition of the relevance of the theory of formal languages to the practice of compiler construction, the theoretical computer science became a cornerstone of virtually every computer science undergraduate degree program. In the early days of computer science, a great deal of time and energy was devoted to the development of basic concepts, design of fundamental algorithms, identification and development of major subdisciplines, and the classification of problems by their difficulty, those activities that actively engaged many theoretical computer scientists. The role of theoretical computer scientists today is to examine fundamental problems of the field through modeling, analysis, and experimentation. Theoretical computer science is a cornerstone for computer science. It underlies many aspects of the construction, explanation, and understanding of computers. Theoretical computer scientists seek to understand the computational phenomena, the expressibility of languages, the design and performance of algorithms, and general limits on computation. Automata theory is the study of abstract computing devices or machines. The stored program computer, the concept that is central to computer science, owes its origins to Alan Matheson Turing, who studied the fundamental nature of computation in the 1930s. Turing's goal was to describe precisely the boundary between what a computing machine could do and what it could not do. His conclusions apply not only to his abstract Turing machines but to today's real machines. In the 1940s and 1950s, similar kinds of machines, which we today call finite automata, were studied by a number of researchers. These automata, originally proposed to model brain function, turned out to be extremely useful for a variety of purposes. In the late 1950s, the linguist Avram Noam Chomsky began the study of formal grammars. While not strictly machines, these grammars have close relationships to abstract automata and serve today as the basis of some important software components, including parts of compilers. Building on the foundations of context-free grammars, Donald E. Knuth and others introduced algorithms and data structures for the efficient and practical parsing of high-level languages, leading to tools such as YARC, thereby enabling the software revolution of the 1960s. In 1969, Stephen Cook extended Turing's study of what could and what could not be computed. Cook was able to separate these problems that can be solved efficiently by computer from those problems that can in principle be solved but in practice take so much time that computers are useless for all but very small instances of the problem. The latter class of problems is called intractable or NP-hard. It is highly unlikely that even the exponential improvement in computing speed that computer hardware has been following Moore's law will have a significant impact on our ability to solve large instances of intractable problems. Now we look into some of the contributions of theoretical computer science to various fields of study. We'll begin with cryptography and secure computation. New techniques for cryptanalysis, such as the differential and linear cryptanalysis, have greatly enhanced our ability to assess the strength of conventional crypto systems, while the development of factorization and discrete logarithm techniques based on the number field sieve provides a deeper understanding of the foundations of public key cryptography. When looking into communication networks, online algorithms and multi-commodity flow algorithms have proven useful for admission control and for routing of virtual circuits in asynchronous transfer mode, that is ATM networks. In the case of computational geometry, techniques from the computational geometry have been used in a variety of other areas of computing. The visibility graphs and the visibility complex have been used in systems for computer vision and computer graphics. Graph drawing algorithms are used in advanced graphic user interfaces and visualization systems. In the case of parallel computer architecture, the algorithm development and the analysis of parallel architectural models, such as the mesh connected processors, hypercubes, cube connected cycles, and butterfly networks, have informed and shaped the design of many parallel multiple processor machines in use today. Now, in the case of software systems, many software systems have incorporated ideas and algorithms first developed in a theoretical framework. For example, evolving algebras have been used to specify languages such as C, Prolog, or VHDL to define real and virtual architecture, for example, APE, PVM, and transporter. To validate standard language implementations, like in case of Prolog, and to validate distributed protocols. Now, looking into programming languages, the methods of structured operational semantics, which derived input both from the lambda calculus and its model theory, reached a point in the 1980s where full-scale languages could be defined in such a way that the properties of the language, like the determinacy of evaluation and the lack of dangling pointers, could be rigorously proven. Now, in the case of VLSI design, the theory of VLSI algorithms and architecture has guided the development of VLSI design. Theory has confirmed that the quality of designs for special problems such as matrix multiplication and convolution has influenced the development of layout algorithms for unstructured problems. And we have the learning theory. Here, algorithms have been developed within the computational learning theory community that learn subclasses of finite probabilistic automata. Now we'll look into the three central concepts of automata theory, which are the languages, grammars, and automata. We'll begin by looking into languages. Dictionaries define the term informally as a system suitable for the expression of certain ideas, facts, or concepts, including a set of symbols and rules for their manipulation. While this gives us an intuitive idea of what a language is, it is not sufficient as a definition for the study of formal languages. We need a precise definition for the term. We'll start with a finite, non-empty set, sigma, of symbols called the alphabet. From the individual symbols, we'll construct strings, which will be finite sequences of symbols from this alphabet. For example, if we have the alphabet sigma is equal to AB, then ABBB and ABA are strings on sigma. With few exceptions, we'll use the lowercase letters ABC for elements of sigma and UVW etc. for string names. So we'll write, for example, W is equal to ABAAA to indicate that the string named W has a specific value ABAAA. The concatenation of two strings W and V is the string obtained by appending the symbols of V to the right end of W. That is, if W is A1, A2, etc. AN and V is B1, B2, etc. BM, then WV will be A1, etc. AN followed by B1, etc. BM. The reverse of a string is obtained by writing the symbols in reverse order. So if W is a string, then WR will be the reverse, AN to A1. The length of a string W is denoted like this, which is the number of symbols in the string. We also have this symbol to denote the empty string, which has no symbols at all. Now, looking into some of the relations, the length of an empty string will be 0 and lambda w is equal to w lambda is equal to w, which holds for all w. Any string of consecutive symbols in some w is said to be a substring of w. For example, if w is equal to vu, then the substrings v and u are said to be the prefix and suffix of w respectively. If w is a string, then w raised to n will stand for the string that is obtained by repeating w n number of times. So a special case of this would be w repeated 0 times, which will give the empty string for all w. Now, if sigma is an alphabet, then we use sigma star to denote the set of strings obtained by concatenating 0 or more symbols from sigma. Now, the set sigma star always contains lambda, which is the empty string. To exclude the empty string, we'll define sigma plus is equal to sigma star minus lambda. Now, while sigma is finite by assumption, sigma star and sigma plus are always infinite since there is no limit on the length of the strings in these sets. A language is defined very generally as a subset of sigma star. A string in a language L will be called a sentence of L. This definition is quite broad. Any set of strings on an alphabet sigma can be considered a language. Since languages are also set, the union, intersection, and difference of two languages are immediately defined. Now, the complement of a language is defined with respect to sigma star. That is, the complement of L is equal to sigma star minus L. The reverse of a language is the set of all string reversals given W raised to R, where W is an element of the language L. The concatenation of two languages L1 and L2 is the set of strings obtained by concatenating any element of L1 with any element of L2, as given here. We define Ln as L concatenated with itself n number of times. A special case of that would be L concatenated 0 times will be lambda. L concatenated once will be L for every language L. Finally, we define the star closure of a language as L star is equal to L0 union, L1 union, etc. And the positive closure L plus is equal to L1 union, L2 union, etc. Now we'll look into what grammar is. Now to study language mathematically, we need a mechanism to describe them. Every day, language is imprecise and ambiguous, so informal descriptions in English are often inadequate. A grammar G is defined as a quadruple. G is equal to V, T, S, P, where V is the set of objects which is finite called variables. T is the finite set of objects called terminal symbols. S is an element of V, which is the start variable, and P is the set of productions. Now it will be assumed that the set V and T are non-empty and disjoint. The production rules are the heart of a grammar. They specify how the grammar transforms one string into another, and through this they define a language associated with the grammar. In our discussion, we will assume that all production rules are of the form x giving y, where x is an element of v union t plus and y is an element of v union t star. Now the productions are applied in the following manner. Given a string w, which is of the form w is equal to u x v, now the production x giving y is applicable to the string, and we may use it to replace x with y. Then the new string z will be u, y and v. So we can write it as this, which means w derives z or z is derived from w. Successive strings are derived by applying the productions of the grammar in arbitrary order. A production can be used whenever it is applicable and it can be applied as often as desired. Now if W1, W2, etc. Wn, we say that W1 derives Wn and write W1 star Wn, which means an unspecified number of steps including 0 can be taken to derive Wn from W1. By applying the production rules in a different order, a given grammar can normally generate many strings. The set of all such terminal strings is the language defined or generated by the grammar. Let G is equal to VTSP be the grammar and the set LG here be the language generated by G, and if W belongs to the language L of G, then the sequence S giving W1, W2, etc. Wn, giving W is a derivation of the sentence W. The strings S, W1, W2, etc. which contain variables as well as the terminals are called sentential forms of the derivation. Now normally a given language has many grammars that generate it. Even though these grammars are different, they are equivalent in some sense. We say that two grammars G1 and G2 are equivalent if they generate the same language, that is, if L of G1 is equal to L of G2. Finally, we'll look into automata. An automaton is an abstract model of a digital computer. As such, every automaton includes some essential features. It has a mechanism for reading the input. It will be assumed that the input is a string over a given alphabet written on an input file which the automaton can read, but it cannot be changed. That is why there is a single directional arrow here. The input file is divided into cells, each of which can hold one symbol. The input mechanism can read the input file from left to right, one symbol at a time. The input mechanism can also detect the end of the input string by sensing the end of file condition. The automaton can produce the output of some form. It may have a temporary storage device consisting of an unlimited number of cells, each capable of holding a single symbol from an alphabet. That not necessarily the same one as in the input alphabet. The automaton can read and change the contents of the storage cells. So it is a bidirectional arrow here. Finally, the automaton has a control unit which can be in any one of the finite number of internal states and which can change the state in some defined manner. Now this is a schematic representation of a general automaton. It is assumed to operate in a discrete time frame. At a given time, the control unit is in some internal state and the input mechanism is scanning a particular symbol on the input file. The internal state of the control unit at the next step is determined by the next state or transition function. This transition function gives the next state in terms of the current state, current input symbol, and information currently in the temporary storage. During the transition from one time interval to the next, output may be produced or the information in the temporary storage may be changed. The term configuration will be used to refer to a particular state of the control unit, input file, and temporary storage. The transition of the automaton from one configuration to the next will be called a move. A finite state control will be common to all specific cases, but the differences will arise from the way in which the output can be produced and the nature of the temporary storage. As we will see, the nature of the temporary storage governs the power of different types of automata. A deterministic automaton is one in which each move is uniquely determined by the current configuration. That is, if we know the internal state, the input, and the contents of the temporary storage, we can predict the future behavior of the automaton exactly. In a non-deterministic automaton, this is not so. At each point, a non-deterministic automaton may have several possible moves. so we can only predict a set of possible actions. An automaton whose output response is limited to a symbol yes or no is called an acceptor. Presented with an input string, an acceptor either accepts the string or rejects it. A more general automaton capable of producing strings of symbols as output is called a transducer. Now we look into some of the applications. Compilers and other translators that convert a program from one language to another make extensive use of the ideas touched here. Programming languages can be defined precisely through grammar, and both grammars and automata play a fundamental role in the decision processes by which a specific piece of code is accepted as satisfying the conditions of a programming language. That's all for now. Thank you for watching.